This Python code is used to install the necessary packages or libraries required for a particular project. First, the sys library is imported, which allows access to system-specific parameters and functions. Then, the pip module is used to manage and install Python packages. The command sys.executable mpip ensures that the correct version of pip is being used, and the install command is used to specify that we want to install the packages. The -r requirements.txt flag indicates that the packages listed in the requirements.txt file will be installed. This file typically includes a list of dependencies or packages that are needed for the project to run properly. By running this code, we can efficiently install all the required packages and dependencies without having to manually install each one. The code first imports various libraries such as SciPy, Patsy, Pickle, NumPy, Pandas, SciPy.sparse, Matplotlib.pyplot, Statistics, SciPy.stats, and StatsModels.formula.api, as well as the TQDM library that allows for creating progress bars. These libraries provide various functions and methods that will be used in the code. Next, the code uses the import statement to access these libraries and make their functions available for use. For example, the from statistics import median statement imports the median function from the statistics library. Finally, the code uses the as keyword to create aliases for these libraries. This allows the developer to refer to these libraries using shorter, more convenient names. For example, instead of writing scipy.sparse.csrmatrix, the developer can simply use scipy.sparse.csrmatrix in their code. Overall, this code is used at the beginning of a Python code to import necessary libraries and make their functions and methods available for use. This Python code initializes a variable named baradir and sets it equal to the path of a directory that contains data for a project. It also creates an empty dictionary called data. Next, it uses a for loop to loop through the year 2004 and sets a variable named fill equal to the file path of the data for that year. The data is then loaded using the pickle module and added to the data dictionary using the update function. The code then creates another empty dictionary named covariance and uses a for loop to loop through the years 2003 and 2004. Similar to before, it sets the variable fill equal to the file path of the covariance data for each year and loads the data using the pickle module. The loaded data is then added to the covariance dictionary using the update function. Finally, the code creates one more empty dictionary named daily return and uses a for loop to loop through the years 2004 and 2005. It sets the variable fill equal to the file path of the daily return data for each year and loads the data using the pickle module. The loaded data is then added to the daily return dictionary using the update function. In summary, this code reads and organizes data from various files in the given directory and stores it in 3 dictionaries named data, covariance, and daily return. These dictionaries are then used to analyze the data for the specific project. This code first initializes an empty dictionary called frames and defines a variable dLi_return n days delay with the value of 2. Then it creates a list of tuples called date shifts using the zip function, which takes in 2 lists of keys from the data dictionary and the daily return dictionary and sorts them. The dLi_return n days delay is used to determine the length of the sorted list. The for loop then iterates through each tuple in date shifts and uses the merge function to combine the values from the data dictionary and the daily return dictionary for a specific price date. The result is then added to the frames dictionary, with the key being the specified price date. In summary, this code is used to merge data from 2 dictionaries into a single dictionary based on a specified price date. This code creates a function that allows input for DLI return date and the variable df in frames. In this function, the number of rows in the df variable is determined and stored in the n-rows variable. Then, a new column called dli return date is created in the df variable, and the pd.series function is used to fill this column with a series of values, with each value being the same as the input dli return date. Essentially, this code is adding a new column to the data frame and filling it with the same value for each row based on the input dli return date. This can be useful for keeping track of when the data was collected or processed, and can also help with organizing and filtering the data based on this information. This code selects the data frame 2004-0108 and then uses the head function to display the first 5 rows of the data frame. This allows the user to quickly view a summary of the data in the selected data frame and get a general idea of its structure and values. The head function is commonly used in data analysis to get a quick visual overview of the dataset before diving into more in-depth analysis. This code defines a function called wins that takes in 3 parameters, x, a, and b. Inside the function, it uses the NumPy libraries where function to compare the value of x to the values of a and b. If x is less than or equal to a, the function returns the value of a. If x is greater than or equal to b, the function returns the value of b. If x is between a and b, the function simply returns the value of x. This function essentially acts as a limit, ensuring that x will always fall between the values of a and b. This can be useful for various purposes, such as limiting the output of a calculation or creating boundaries for a variable. This Python code creates a density plot for a specific dataset of daily returns. It first defines a function called density plot that takes in the dataset as a parameter. Within this function, it uses the Gaussian KDE function from the scipy.stats library to create a density estimation for the data. The range of values for the density estimation is determined by the minimum and maximum values in the dataset, with 200 evenly spaced points in between. A covariance factor of 0.25 is set for the density estimation, and then the covariance is computed. The plot function from the matplotlib library is then used to create the actual density plot, plotting the data values against the density estimation. The x-axis is labeled as daily returns and the y-axis as density. Finally, the plot is shown using the plth.show function. The last two lines of code, starting with test equals frames 2004-118 and ending with density plot as dli return, are used to test and visualize the density plot for a specific date, in this case, January 8, 2004. The data for that specific date is extracted from the frames dataset, and then a wins function is applied to it. This function assigns any values below -0.1 to 0.1 and any values above 0.1 to the value 0.1, essentially limiting the range of values for the dataset. This updated dataset is then passed into the density plot function to create the density plot for that specific date. This allows for visualizing the distribution of returns for a specific date compared to the overall dataset. This Python code is designed to estimate factor returns using ordinary least squares OLS regression. The first function, getFormula, takes in a list of factors and a dependent variable and returns a formula for the OLS regression. The second function, factorsFromNames, filters out all factors that do not contain the string useFastD and returns a list of the remaining factors. The main function, estimateFactorReturns, first creates a copy of the given data frame, limiting it to only include data from companies with a market capitalization above $1 billion. It then applies a winsorization process on the daily returns, which means it limits the returns to fall within a specified range. Next, it calls the factorsFromNames function and assigns the returned list of factors to the variable allFactors. This list is then used as an input for the getFormula function, along with the dependent variable dli return. The OLS function from the statsModels library is then called, passing in the formula and the data from the filtered universe. The results of the regression are stored in the variable results and returned at the end of the function. In summary, this code is a systematic way to estimate factor returns using OLS regression, utilizing functions to create the necessary formula and filter out relevant factors. This code snippet creates an empty dictionary called facret and then iterates through a list called frames, assigning each element in the list to the variable date. Within the for loop, the code then uses the estimateFactorReturns function to calculate a set of parameter estimates based on the given date in the frames list. These parameter estimates are then assigned as values to the facret dictionary, with the corresponding date as the key. In essence, this code is creating a dictionary that maps each date in the frames list to its respective factor return estimates. This code sorts a list of dates by converting each date from a string with the format %y$d into a datetime object using the pd to datetime function. It does this by first applying the map function to the frames.keys list, which creates a new list by executing the pd datetime function on each element in frames keys. The result is then passed to the sorted function, which arranges the dates in ascending order. The sorted dates are stored in the myDates variable, which can then be used for further processing. Overall, this code is useful for organizing dates in a dataset and being able to easily access and work with them in chronological order. This Python code creates a list of alpha factors used in financial analysis and assigns them to a variable called alpha factors. It then uses the pandas library to create a new data frame called facretDF with the dates as the index. The code then loops through each date in the list of dates and each alpha factor in the list and assigns the corresponding return value for each factor on that date to the facretDF data frame. Next, the code plots the cumulative returns for each alpha factor over time and displays a legend in the upper left corner. Finally, the code labels the x and y axes and displays the plot. Essentially, this creating a visual representation of the cumulative returns for each alpha factor over a specific period of time. This Python code is a function that takes in a data frame and removes all the null or missing values from its numeric columns. It first identifies the numeric columns in the data frame using the selectDtypes function and stores them in a list. Then, it iterates through each numeric column in the list and replaces any null values with a numerical 0 using the np.nan-to-num function. Finally, the clean data frame is returned as the output of the function. This code would be useful for data cleaning and preparation, as missing values can often cause errors or bias in data analysis. This code first creates a pandas data frame called previous holdings with two columns, Barrett and h.previous. The Barrett column has one value, USA02P1, and the h.previous column has a numpy array with a single value of 0. This data frame is then merged with another data frame called df, using the Barrett column as the key to create a new merged data frame. Any missing values in this merged data frame are then cleaned by replacing them with the median value of the spec risk column. Finally, any rows in the spec risk column with a value of 0 are replaced with the median value of the entire spec risk column. This code essentially creates a new data frame by merging two existing data frames and then replaces any missing values and 0 values in the spec risk column with the median value. This code defines a function called getUniverse that takes in a data frame as a parameter. The purpose of this function is to create a stock universe, which is a collection of stocks that meet certain criteria or filters. The function first creates a new data frame called universe and assigns it the filtered data frame from the input parameter. This filtering is done using the lock function, which selects rows that meet the specified conditions. The first condition checks if the value in the issuer market cap column is greater than or equal to 1,000,001E9 in scientific notation. The second condition checks if the absolute value in the h.previous column is greater than 0. The operator represents a logical OR operation, meaning that the row must meet either one of these conditions to be selected. The resulting data frame is then copied to the universe variable. The next line drops the DLI return column from the universe data frame. Finally, the function returns the universe data frame, which is then stored in a variable with the same name by calling the getUniverse function with the input data frame df. Overall, this code creates a stock universe by selecting stocks from the original data frame that meet the specified filter conditions. This line of code converts the second value from the data-date column in the universe variable into an integer using the int function. It then converts the integer into a string using the star function and assigns it to the variable date. The overall purpose of this code could be to convert a date stored as a string into an integer and then back to a string for easier manipulation or calculation. This Python code takes a list of names called universe and converts it into their respective factors. The factors from names function uses the list of names as input and returns a list of factors based on each name. These factors can potentially be used for further analysis or calculations. The list function is used to convert the input into a list, and the universe variable represents the original list of names. The output of this code is a list of factors called all factors. This code could be useful for categorizing and organizing data based on the names in the universe list. For example, if the names in the universe list represent different products, the resulting factors could represent categories such as electronic, furniture, or clothing. Overall, this code allows for efficient and automated data manipulation and analysis by converting names into factors. This code creates a function called setDiff that takes two parameters, temp1 and temp2. On the first line within the function, a new set called s is created using the elements from temp2. This is done using the set function, which removes any duplicates and orders the elements in the set. On the next line, a new list called temp3 is created using a list comprehension that iterates through each element in temp1. The condition for the comprehension is that the element must not be in the set s. This means that only elements that are present in temp1 but not in temp2 will be added to the new list. Finally, the function returns the list temp3, which contains all the elements from temp1 that are not in temp2. Overall, this function can be used to find the differences between two lists. This code creates a new set called risk factors by taking the set difference between two existing sets, all factors and alpha factors. The set difference operation removes any elements from the first set all factors that are also present in the second set alpha factors, resulting in a set containing only the elements that are unique to the first set. In this case, the code is likely being used to identify the risk factors that are specific to a certain domain or problem by removing any elements that are considered to be standard or known factors represented by the set alpha factors from a larger set of potential factors represented by all factors. This could be useful in a variety of scenarios, such as identifying which factors are contributing to a particular issue or determining which factors should be prioritized for further analysis. This line of code accesses a value from a variable called universe. The value being accessed is the one associated with the key h.t.previous. This value is stored in a variable called h0. It is likely that universe contains a dictionary of values, and h.previous is one of the keys in this dictionary. The value being accessed could be anything, but based on the variable name and the opt in the key, it is possible that this value has something to do with options or settings. By storing this value in a variable and giving it the name h0, it can be easily referenced and used in the rest of the code. This code calls a function called getFormula and passes in two arguments, risk factors and spec risk. The getFormula function likely calculates a mathematical formula based on the given risk factors and returns the result. The first argument, risk factors, is probably a dataset or list of risk factors that are used to calculate the formula. The second argument, spec risk, likely refers to a specific type of risk that is specifically being evaluated in this formula. Overall, this code is calling a function and passing in the necessary information to calculate a formula based on a specific risk factor. This Python code creates a model matrix using the formula and data provided as input. The function patsy.dmatrices takes in the formula and dataces, one for the outcome and one for the predictors. The outcome matrix contains the response variable, and the predictor matrix contains the input variables or features that will be used to predict the outcome. These matrices are then stored in the variables outcome and predictors. Finally, the function returns the predictor matrix, which can then be used to train a model to predict the outcome variable. This code is using the function's model matrix and transpose to first create a matrix, B, based on a formula and a given universe. The formula likely describes a mathematical relationship between variables. This matrix stores numerical data that represents this formula. The model matrix function calculates this data, and the universe parameter specifies which values to use for the variables in the formula. Next, the transpose function is used to create a new matrix, BT, which is the transpose of B. This means that the rows and columns of B are swapped, resulting in a new matrix with the same data, but in a different configuration. The purpose of transposing B is to potentially make it easier to manipulate or analyze the data, depending on the specific needs of the code. Overall, this code is likely part of a larger code or algorithm that is using the model matrix and its transpose to perform various calculations or analyses. This code retrieves the first two values from the spec risk column of the dictionary or data frame named universe. The use of square brackets 0, 2 indicates a range of indices to be retrieved, starting from index 0 and stopping before index 2. Therefore, this code returns the first and second values of the spec risk column in the universe dataset. This could be useful for analyzing a specific subset of data or for further manipulation and analysis. First, the code creates a variable spec var and assigns it a value. It takes the value of a specific risk attribute from a dictionary called universe and multiplies it by 0.01. The resulting value is then squared. This operation is useful in calculating the variance for a specific risk in a portfolio, as it allows us to compare the amount of risk taken with other assets. The smaller the value, the less risky the asset is, and vice versa. Overall, this code is a useful tool in risk management and decision-making for investments. This code accesses the covariance dataset and retrieves the data for January 2, 2004. The .head function is then used to display the first few rows of data for that particular date. Overall, this code allows for easy and efficient retrieval of specific data from the covariance dataset. This function, named colnames, accepts a single argument named B. This function first checks the type of B, and if it is of the patsy.designinfo.designMatrix type, it will return the column names associated with the B variable. If B is not of this type, the function checks if it is of the pandas.coreFrame.DataFrame type. If it is, the function will return a list of the column names for B. If B is not of either of these types, the function will return none. In summary, this function checks the type of the input and returns the column names associated with the input if it is of a particular type. This Python code calculates the factor covariance matrix given a specific date and a matrix of risk factors. The diagonal factor cov function takes in two parameters, date and B. The date parameter is a string representation of a specific date, while B is either a patsy.designinfo.designMatrix or a pandas.core.frame.DataFrame that contains the risk factors. The function then creates an empty numpy array called fm, with the size of the array being determined by the number of risk factors in B. Then, a for loop is used to iterate through each risk factor in B. For each risk factor, the code calculates the variance by retrieving the covariance value from the specified date and multiplying it by 0.01 squared, converting from percentage units to decimal units. This variance value is then stored in the corresponding index in the fm array. Once the loop is finished, the function returns the fm array, which contains the factor covariance matrix. This matrix can then be used for other calculations or analysis. The given code takes in two inputs, the universe data frame and a specific column name, which defaults to ADT-SINA30. It then uses the pandas lock function to locate all rows in the universe data frame, where the column specified in composite volume column is filled with null values represented by np.isnan, and replaces those null values with the number 1.0e4 equivalent to 10,000. Next, it locates all rows in the universe data frame where the same column has a value of 0, and replaces those values with 1.0e4 as well. Finally, it creates a new variable, addv, which is equal to the values in the specified column of the universe data frame. The code then calculates a value for lambda by dividing 0.1, representing 10% by the values in addv. This value for lambda is returned by the function and assigned to the variable lambda. Overall, this code ensures that null and zero values in the specified column are replaced with a large number to avoid any errors in subsequent calculations, and then calculates a value for lambda based on the column values. The above code defines a function called getBalpha that takes two parameters, alpha factors and universe. The function then uses these parameters to create a model matrix by calling another function called getFormula with the parameters alpha factors and spec risk. This model matrix is then applied to the data found in the universe parameter. Finally, the function returns the result of this model matrix as B-alpha. The last line of the code uses the getBalpha function to assign the result of the function to the variable B-alpha. In simpler terms, this code is creating a function that generates a particular type of matrix using the given parameters and applies it to a specific dataset, with the resulting matrix being stored in a variable called B-alpha. This code is a function called getAlphaVec that takes in a matrix of alpha factors called B-alpha and returns an alpha vector. First, the function initializes a variable called scale, which is set to 1e-4. Next, it uses numpy to sum up the values of the matrix B-alpha along the rows axis equals 1 and multiplies it by the scale value. This result is then assigned to the variable alphavec and returned as the output of the function. Finally, the function is called with the same input matrix B-alpha, and the returned value is assigned to a variable called alphavec. This code sets up a function to calculate the objective function for a given set of parameters. The function takes in the initial values of h0, the risk aversion, q, specific variance, alpha vector, and lambda. Inside the function, there is an implementation for the objective function, which is initially set to 0. The objective function is then calculated by adding together different components, including the squared matrix multiplication of q and h, the squared element-wise multiplication of h and specific variance, a dot product of h and the alpha vector, and the squared element-wise difference between h and h0 multiplied by lambda. The risk aversion is used to weight the different components, with a smaller value indicating a lower risk tolerance. Finally, the complete objective function is returned to be used in the optimization process. This code defines a function called getGradFunc that takes in several input parameters, including h0, risk aversion, q, qt, specvar, alphavec, and lambda. The function then defines an inner function called gradfunc that takes in one parameter called h. This inner function uses the input parameters to perform calculations and return a numerical solution. The calculation involves matrix multiplication, addition, and subtraction, and appears to be related to a mathematical optimization problem. The result of this calculation is then returned as a NumPy array. Finally, the outer function getGradFunc returns the inner function gradfunc as its final result. Overall, this code likely represents a specific implementation of an algorithm or mathematical formula used for data analysis or modeling. The above Python code aims to optimize the objective function of a trader, given the trader's risk aversion, Q matrix, the transpose of the Q matrix, specific variance, alpha vector, initial holdings, and lambda. The overall goal is to find the optimal holdings H star that will maximize the objective function. Firstly, the code defines the values for risk aversion and Q. Then, it calculates the square root of the variance-covariance matrix FVAR using the SciPy library and multiplies it with the transpose of the Q matrix to get the Q transpose matrix QT. Next, the code defines a function named getH*, which will be used to optimize the objective function. The function takes in the trader's risk aversion, Q matrix, QT matrix, specific variance, alpha vector, initial holdings, and lambda as parameters. It then calls two other functions named getObjFunc and getGradFunc to calculate the objective function and gradient function, respectively. After that, the code uses the SciPy.optimize library's fmin_lbfgsb function to optimize the objective function, and the result is stored in the optimizer result variable. This function uses the limited memory Broyden-Fletcher-Goldfarb-Shano-lbfgsb algorithm to find the optimal solution to the objective function. The optimized holdings H* are then returned as a NumPy end array. Finally, the code calls the getH* function with the required parameters to obtain the optimized holdings H*. The H* is then used for further calculations and analysis in the code. The first line creates a pandas dataframe object called opt_portfolio and sets it equal to the result of a function call. The function being called is pd.dataframe, which creates a dataframe object when given data as its input. In this case, the data being used is a dictionary with two columns, barid and h_opt, and their respective values being pulled from an existing variable universe. The barid column contains the values from the barid column in the universe variable, while the h.opt column contains the values stored in a variable called h*. This code essentially takes data from an existing variable and creates a new dataframe object with that data, but in a format that is easier to manipulate and work with. This code is a function called getRiskExposures that calculates the risk exposure of a portfolio using three input variables, B, BT, and H*. B is a matrix of risk factors, BT is the transpose of that matrix, and H* is an optimized holding. The function uses Patsy design info, design matrix, and NumPy to calculate the risk exposure parameters. The result is then stored in a pandas series called risk exposures and returned as the output of the function. Overall, this function is used to calculate and provide a quantitative representation of the portfolio's risk exposure, which is important in assessing and managing investment risk. This Python code defines a function called getPortfolioAlphaExposure, which takes two inputs, B alpha, a matrix of alpha factors, and H*, an optimized holdings array, and calculates the portfolio's alpha exposures. This function then returns a pandas series containing these alpha exposures. The function uses the NumPy library to perform matrix multiplication between the transpose of the matrix B alpha and the holdings array H*. It also includes a to-do comment to remind the user to implement this function. Finally, the code creates a variable called portfolioAlphaExposure, which stores the result of the getPortfolioAlphaExposure function using the inputs B alpha and H*. This code defines a function called getTotalTransactionCosts, which takes in three parameters. H0, which is a pandas series representing the initial holdings before optimization, H*, which is a NumPy end array representing the optimized holdings, and lambda, which is a pandas series. Inside the function, total transaction costs is calculated by taking the dot product of the squared difference between H* and H0 and lambda, and then summing up the result. This result is then returned by the function. Outside the function, the total transaction costs variable is assigned the value returned by calling the getTotalTransactionCosts function with the three parameters specified. In summary, this code calculates and returns the total transaction costs based on the initial holdings, optimized holdings, and lambda values provided. This code is used to form an optimal portfolio for investing based on a given dataset and risk aversion level. The DF parameter represents the dataset containing information about different assets, including the spec risk-specific risk of each asset. The previous parameter is the previous optimal portfolio, which is used to calculate the transaction costs of rebalancing the portfolio. The risk aversion parameter represents the level of risk aversion of the investor, which is used to determine the optimal portfolio weights. The first two lines of code merge the previous portfolio information with the dataset, and then clean the dataset by removing any rows with missing values. The next few lines of code calculate the median spec risk and use it to fill any missing values for this column in the dataset. The universe variable represents the subset of the dataset that will be used for the optimization process. Next, the code calculates the factors that will be used in the risk model, including all factors and alpha factors that are expected to outperform the market. The H0 variable represents the previous optimal portfolio weights, while B and BT are matrices used to calculate the overall risk factor and covariance matrix. The spec_var variable represents the specific risk of each asset, which is used in the calculation of the optimal portfolio. The FVAR variable represents the factor covariance matrix, and lambda is a factor risk penalty parameter. The code then uses these variables to calculate the optimal portfolio weights, considering the risk aversion of the investor. The resulting portfolio is saved in the opt portfolio data frame. The next few lines of code calculate the risk and alpha exposures of the portfolio, as well as the total transaction costs of rebalancing the portfolio. Overall, this code uses various calculations and parameters to determine the optimal portfolio weights for investing, taking into account the investor's risk aversion and transaction costs. The above code is a function that takes in two arguments, namely prev holdings and opt result. It is likely a part of a larger code or project that deals with some kind of trading strategy or analysis. The purpose of this function is to build a trade list using the data from the previous holdings and the opt result, which contains information about the optimal portfolio. The first line of the code initializes a temporary variable named TMP. This variable is set equal to the result of merging the previous holdings and the optimal portfolio using the outer merge method, and the common column being used for the merge is buried. This means that the resulting data frame will contain information from both the previous holdings and the optimal portfolio, with any non-matching values being filled with null values. The next two lines of code use the NumPy library to convert any null values in the h.previous and h.opt columns to 0. This is done to ensure that the trade list being built does not contain any null values, as this could cause issues with further analysis or processing. Finally, the function returns the temporary variable TMP, which now contains the trade list with all the necessary information from both the previous holdings and the optimal portfolio. This trade list can then be used for further analysis or implementation of a trading strategy. This Python code takes in a variable called result and uses its dictionary key opt.portfolio as the input to a new variable called prev. Then, the code renames the index of prev to be of type star and changes the column name from h.opt to h.opt.previous. This new variable is then returned as output. Essentially, this code converts the column headers and index of the original input into the previous version of itself, possibly for use in further calculations or analysis. Overall, this code can be used as a helpful tool for organizing and manipulating data. This code is part of a code that is optimizing a portfolio for a given set of dates. The first line initializes two empty dictionaries, trades and port,